Go off. Hello. Hi everyone. My name is Stella Waidera.
So,
Welcome to the Africa STEM Summit 2024. Welcome to day two. Um, Today we are going to be learning backend, designing, database design and development. Um, on the Our speaker is Steve Otieno. Steve Otieno is a Python developer and a full stack developer as well. He also doubles as a computer science instructor and a curriculum developer. So the main goal of the Africa STEM Summit is to technically equip you with senior level to intermediate to junior level knowledge. And I am going to pass the mic to Steve. So hi, Steve. And Steve, you're muted.
hello everyone. Yeah,
Hello.
thank you for joining this section. I hope it's going to be interactive, and you guys are going to. Hello, hello. Yeah, I hope you can hear
Hello.
me.
Yes, we can hear you. You can proceed.
Mic check.
Hello, Steve. We can hear you clearly. Kindly proceed. Hello, Steve. We can hear you. You're muted. Hello, Steve. You're now muted. Kindly unmute yourself. Okay, so guys, let me just alert Steve that he's muted. I think he doesn't know that he has muted his mic, and then we can proceed with the session. So maybe as Steve is joining in, you can let us know where you are joining us from. Where are you tuning in from? For this session, which level are you in backend development? Are you a junior? Are you a senior? Or are you intermediate? So just a minute.
Mic check. I hope you guys can hear me well. Hmm.
Yes, we can. Kindly
The
proceed.
topic was database design and development. Now, I think Estella and Cassandra have done a befitting introduction for me, and judging from time, I think we should just kick this off. Okay. Now, database design and development is a very essential part of software development. At the end of the day, we usually have three tiers of an application's architecture. So we usually have the database on this side. We usually have a backend somewhere here. Then we usually have the front end somewhere. So there's the backend, front end, and the database. So everything we're doing from the front end to the back end, we're doing it because we want to store and manage that data well. And so it should go without saying that if we get the data part wrong, then we are going to get a lot of other things wrong on the front end and the back end. I think this arrow should have faced this other side. Yeah, so if we get this bit wrong, so we are going to have a lot of mistakes on this other side because maybe data won't be stored appropriately and won't be retrieved appropriately. Now, when we talk about database design and development, we usually divide it into three parts. There is the conceptual, there is the logical, and there is the physical. So these are the three sections in which database design is divided into. Now, with conceptual, we're interested in high-level details. With logical, we move into more finer details, intricate details concerning architecture and that is relevant to the specific architecture you're going to use to implement that design. So now with conceptual, it's high level, and we are interested in our interest is in entities and their attributes. That is with conceptual. How did I miss an A here? We said in entities and their attributes. With the logical, we are interested in the attributes and the. Now, it's also important for me to note that at this particular level, you're also interested in the relationships. The relationships, different attributes. So in the relationships between the different all domain. So this is a system concerning like a school this way. So now this system here is going to have entities. Entities are just the real world objects that we are interested in depicting in our system. So for example, for a school database, an entity will be like a student, an entity will be a teacher, an entity will be like the examination, an entity will be like a department. Now these are the some of the features of a school that we may be interested in storing information about. So for the conceptual one, as I mentioned, interested in high-level entities and their attributes. Now, in some designs, you'll notice that in conceptual, we don't include the attributes, which is also okay. And on my bit, I'll also just get rid of the attributes so at least we can focus on just the high-level entities and their relationships. Now, with the logical one, we now get into the entities, attributes, and the types. Now, it is at this level where we look at normalization. So there's the entities, attributes, and the types, and normalization is also done here. Now, in the physical design, we are now down with the conceptual and the what do you call the conceptual and the logical. Now, we get into a specific implementation. For example, if you decide to use MongoDB, of course, its type will be a little bit different from if you're using relational database. Now, the physical one is now based on that specific architecture type that you're going to use to implement your database design. So it could be a relational database, it could be any other. So here now we are more specific with types. That way, they are more specific with the types. Now, in this case, we are also going to implement it based on a particular architecture. We implement based on architecture. It's architecture or a specific DBMS. Now, of course, that architecture will have its own types. Now, if you're using a relational one, the data types will have been different as opposed to if you're using a document database, and then it's also different if you're using a what do you call it, a hierarchical database. The implementations are going to be a little bit different as opposed to just the different types that are available. Now, since we started with the school, I think we'll proceed with the school. So for the conceptual design for the school system, we'll have the entities. Most of the time they're usually drawn. Usually use this. So I'll use this to depict the student. So the student is an entity, and then there is a relationship between the student and a teacher that way. So now we just draw the high level entities, the student and the teacher in this case. Now there'll be a relationship between them. When you talk about relationships, there are different degrees of relationships with reference to DBMS. So the relationship can be one to one, it can be a one to many, it can be a one to many, it can be a many to many. Now, I usually see some people also depict that fact that there's also a many to one, which is true, but it just depends on where we place one entity. That is why we can talk about the one to many or many to one. But the concept of one to many and the concept of many to one is just the same. The only difference is where does the one entity exist? Is the one entity on the left or is it on the right? Now, for the student-teacher kind of relationship, we have many to many kind of relationship between these two. So we'll use this notation. This notation is known as the cross-foot notation. There's also a chain notation and some other notation, but this is a cross-foot notation. Of course, it doesn't look like the feet of a crow. As you can see, that's why probably they named it a cross-foot notation. So there's a many-to-many relationship between the student and the teacher. Now, if you want to be a little bit more specific with, if you want to be a little bit more, if you want to understand better how these things work, it's just the answer to the question: how many instances of the student can appear in the teacher, and how many instances of the teacher appear in the student? Or rather, we can ask it this way now: how many teachers can teach one student? Of course, one teacher is going to teach many students. Then you come to the student side. So how many students can be taught by one teacher? So of course we'll get also the answer to that. So maybe it's maybe one teacher can teach many students, and one student can be taught by many teachers. So that gives us the one to many kind of relationship between the student and the teacher. Now, there's also a relationship between the teacher and the department. Now, probably in our scenario here, let's say one teacher belongs to a particular department. So this is department this way. So department and teacher, what is the relationship? Now, in a scenario where a teacher can only belong to one department, it's going to be a one to many kind of relationship. So one teacher can belong to many departments, as I've depicted it here, as you can see. So this is a relationship between the teacher and department. It is a one to many. One teacher, this simply means one teacher can belong to many departments, but I wanted to depict the fact that one department can have many teachers. So in this case, it is, yeah, it should be a one teacher, one department, many teachers. So I need to add this one to this other side. So one department can have many teachers. So the many part will appear on this side. So one department, many teachers. That is how we are depicting this relationship. There's also a one-to-one kind of relationship. So a one-to-one kind of relationship could be, for example, a student has a bio. So let's talk of the bio for the student. Student has a bio that way. Suppose a student is only going to have one bio. A student is not going to have multiple bios. So this is going to be a one-to-one kind of relationship. So most of the time we draw that one here and that one here. In this case, we also have that many bit here and that many bit on this other side. The many bit here and the one bit on this other side, one to many. So this way we've done a conceptual design. So we are listing the entities, that is the real world objects that exist in that domain, which in this case is a school, together with the relationships between them. So this is a conceptual design. Okay. Before I proceed, I'm not sure if there are any questions so far up to wherever I've reached. So, Cassandra, if there are, maybe you can share with me. Okay. Seems there are none, eh? Seems there are none at all. Okay, it seems there are no questions yet, so we'll proceed. Now, there's a student, there's a teacher, there's the bio, there's the department. Now, when we move to the logical design, we're now going to be a bit more granular with the details. So, what do we want to store in student? What do you want to store in teacher? What do you want to store in bio? What do you want to store in department? So, with this, with the logical design, what we'll simply do is that we'll add the attributes of that particular entity. So, in this case, our student will have a name. Our student will have maybe a course they're doing. Our student will also have maybe an email and a few other things, as you can see here. So now, in this case, now we'll be listing the attributes, the entities, sorry, the attributes of that entity. And then, as I also mentioned, we also list the types. So this is types at high level. So in this case, this could be a string. In this other case, this could also be a string. In this other case, this could also be a string. Now, a student also has a registration number, which in this case could be of the number type. So these are the examples of the the attributes of this particular entity. So we'll list them for all of them, and that the specific type it could be at high level. Now, of course, this is also where we do the normalization bit. So I'll just move on until I finish physical, is when I'll come back to what normalization looks like. Now, there is also the teacher entity, which contains the name, which is a string. There is the course the teacher is teaching. There is the course the teacher is teaching. Then there are some, maybe there is payment details for the teacher. Let's call it salary. It's illegal to talk about teacher, not also talk about salary. It's very, very illegal. So salary could be a float type that way. There is also the name, course, the salary. So the course here could also be a string. Then the salary is a float. Maybe qualification for that particular teacher is also a string that way. Maybe. So far, so good. This database design is very poor, but when we shall get the normalization bit, we shall see why we need to do a few tweaks on this so that at least it looks a little bit better. Now, the other one is you also had a department. So department is going to have a name, which in this case will be a string. A department is also going to have an department ID. Let's just department ID, which could be a number. Department, there is name, ID. Department can also have the department head, which will also be a string that way. So this is an example of logical design. List the entities, the attributes, and the types. And then this is also where we do the normalization. So I think it would be fair to do the normalization bit here now. Now, we have student, teacher, and department. Now, what I'll simply do is to add them to a simple Excel sheet, so that we see at least how it will look like once we start designing. So at least when I'm getting to normalization, it doesn't look very complex. So in this case, we've added, what do you call it? We've added a student table. So a student table, this was the entity, and then it has some attributes. There is the name, there's the course, there's the email, there's the registration number. So there's the name, there is the email, there's the course, there's the registration number. So these ones here are some the attributes of that particular student. Now, let us add an instance of a student. Let us add an instance of a student. In this case, let's say our student is, say for example, Alan Turing that way. Then the email is maybe a.turing at maybe y.com that way. That is the student's email. Let me expand this a bit. Let me see. Why am I having trouble expanding this? Yeah, this should be okay. So I'll be using this at least to depict this simple entity. Now, the course, maybe Alan Turing is doing C, computer science. Registration number maybe is 1 that way. Now, when you're doing normalization, there are a few things we should look at when doing normalization in terms of how this data is being depicted. So in this case, let me just write a few steps for normalization. So in normalizing, there are just a few steps we go through as we design order to ensure that at least we are going to reduce, if not eliminate, the redundancy. So in normalization, there are three steps. There's the first normal form, there's the second normal form, and there's the third normal form. Third normal form. Let me do that in the third normal form. So in first normal form, there are a few things we should look at. So the first one, each instance. So instance is an occurrence of that particular entity. An occurrence could be, for example, we have student 1 whose name is Alan Turing. Another occurrence could be for example, student 2 whose name is Ada Lovelace. Another example could be student 3 whose name is Charles Babbage. So these are examples of a few instances, the occurrence of that entity. Now, each instance should be unique. If not unique, it should be what do you call it? We should have you should have a way of identifying it uniquely. Today doesn't seem to be my lucky day. Today doesn't seem to be my lucky day. What just happened? Why am I struggling with just pushing this on this other side? Anyway, just work with it this way. So each instance should be unique. Another step in normalization. Change it here. I don't know, I'm struggling with this. All of a sudden, it's as though my knee is frozen. Anyway, just select another one. Place it here. So 1NF, the first normal form. The first normal form. I'm struggling with this. Just a moment to figure out where the problem could be. Yeah, I think I've sorted it. Just had one sticky key. So each instance should be unique, and then the columns should the rows of the column. Anyway, let's talk of each cell. Cell doesn't look at each cell. Field. The field is the term. Each field should have an atomic value. It's first normal form. Each instance should be unique, and then each field should have an atomic value. So now let us look at our data and see where the problem could be. In my case, of course, I'm uniquely identifying this row using the registration number. So of course, there is that uniqueness. Now, what we violated here is each field should have an atomic value. So in that case, now, if I come to my data where there's Alan Turing, this value is not atomic. These are two values. So if you update first name and you update last name, you also have to grab all of that, the first name and the last name, then update either the last name or the first name. So this one here violates the rule of the first normal form, such that each field should have an atomic value. So the solution is to have this one be the first name, then this other one be the last name that way. Then of course Alan will come on this other side. So now things are okay. As you can see, things are okay. So if I want to make this one bold, so now by separating the name column into first name and last name, we've ensured that each field is only going to store an atomic value, one single value, not two values. Yeah. So that is okay. So now our table should be in first normal form because we are uniquely identifying it with this primary key, which is the registration number, And then we only have atomic values, as you can see here. We only have atomic values. Now, the next step, let me see. Should be unique. Should be unique. Let me add identified by a primary key that way. That is the first normal form. Not sure if there are any questions so far. Yeah. Good. Seems there are no questions so far. So I'll proceed. Now, in the second normal form, we are supposed to remove something known as, we remove partial dependencies that way. So by removing partial dependencies, they are just some attributes that don't entirely depend on the primary key. So most of the time, if you want to notice what partial dependency is, it is usually a repeating group. A repeating group. That is a partial dependency. So now it is a repeating group because it is not entirely dependent on the primary key. So with the second normal form, we remove the partial dependency of the repeating group. Repeating groups. Now, how does a repeating group look like? Now, if I go back to my data here and I add another instance, let's say Alan Turing now wants to do another course. So Alan Turing wants to do maybe IT. So Alan here, we'll have to add again. So let me just add IT first of all. So now some Alan Turing wants to do IT. Now, since Alan Turing is doing IT, then of course these other fields, we can't leave them empty. We'll also still have to fill them here. We also have to fill this on here, this way. Then we'll have to repeat this, which is violating the primary key constraint. That means every field should be unique. So now, as you can see, the course here is going to depend on whoever is doing that particular course, but it is not entirely dependent. It's just partially dependent. It's not fully dependent on it. So if Alan Turing decides to do another course, now you see we are going to repeat this data for all instances of Alan Turing. For, let's say now he decides to do business, business management that way. So now you see we are repeating all this data. That is the first name, the last name, and the email, because of this new course that Alan Turing wants to do. This new course that Alan Turing wants to do. So course here is a partial dependency because it is not entirely dependent on what? That person. It is partially dependent on that person. So course will exist and is tied to that person or not, but not entirely. So the solution, we create a new table. We create a new table. We create a new table for the repeating groups, and does this keep this? New table for the repeating groups, and join them, join it with a foreign key. That way, this is the solution. So for all the repeating groups, that is what we do. So in my case here, I'll have to create a new table for the course. So I'll come here and create. I think I should close this one. Create a new table for the course. So now should have been up here. So for course, I think this should be enough. Let me create course here because I need something in the middle there. So I'll create a new table for course. a new table for course. So the course will have a name and an ID. So maybe the course is computer science, the course is IT, the course is business management. So this one has an ID of 1, this one has an ID of 2, this one has an ID of 3. So now, of course, now we have to remove this one here, that way. So I think I'll just delete that cell that way. So now, of course, there's this one here, there's the course table, and there is the student table. So now, when you go back to cardinality, this particular point, of course, we didn't have student and a course. Now, the relationship between a student and a course is a many-to-many kind of relationship, because one student can do many courses, and then one course can be done by many students. I'll copy this, then I'll add this one here. So that way. Then there's a relationship between a student and a course this way. So it's a many to many kind of relationship between the student and the course. Now, since it's many to many, the way we usually incorporate a many to many kind of relationship is by using a join table. So a table in the middle here joins those two. It's known as a join table. So a join table for the student and the course would look something like this. Tuite student course hivyo. Student course hivyo. So student course will have the course ID, and it will also have the let me add course ID on this other side. Okay, underscore ID, and then it also have the student ID that way. So we have those two. So the student course table has the student ID and the course ID. So now, if student 1 here, I think now I can get rid of these ones here. They're not necessary. I'll take care of them later. So now, if the student with the ID of 1, let me add another Charles Babbage. That way. So c.b@y.com that way. The student with the registration number 2. Is I cannot forget about other Lovelace that way. So a.l@y.com that way. Then registration number of 3. So for the student and the course, now it will be student course. So the student will have an ID of 1, the course will have an ID of 1. So this one simply means that the student with the ID of 1 is doing the course with the whose ID is 1. So it simply means that Alan Turing is doing the computer science course. Then for Charles Babbage, let's say he's doing another course, business management. So student with the ID of 1 is also doing business management, which has the ID of 3. Keyboard has very sticky keys for Mobutu. ID of 3 that way. And then the student with the ID of 2 is doing the course with the ID of 1. The student with the ID of 3 is doing the course with the my 3 here is very sticky today. The student with the ID of 3 is doing a course with the ID of 2 that way. So now, as you can see, this many-to-many relationship ensures that at least there's not that redundancy in our data. Because now, assuming the student ID existed here, what will happen is that when we add the student with the ID of 1 here, and then he's doing another course, we'll have to repeat other details for that particular student. So we'll have one ID 1 here, ID 2 here. If another student is doing computer science, let's say, for example, let's assume we want student ID here. So now I'll give this one red and bold. So if you have student ID here, let's say student 1 is doing this course with the ID of 1. Now, if student 2 is also doing the course with the ID of 1, then we'll have to add 2 here, and then we add CS again, and then we add 1 here. So you see, now we are repeating this data because another student is doing it. So the join table gives us helps us prevent that insertion anomaly. Insertion anomaly is when we are we are intending to insert one value, but we have to insert other multiple values because of that one value we're inserting. So in this case, if student ID existed here, it will simply mean that we'll have to insert this CS value for all the other. If another student decides to do another course here, we'll have to add even the course details because of that data that we're inserting. So to prevent such an anomaly, we usually separate a many relationship in a different table known as a join table. So this is a join table, this student course table. So now this one here is very unnecessary. That way. Yeah, so this is why we use a join table. So I think we're done with the first normal form and the second normal form. The next one is the third normal form. So with the third normal form, sorry, I haven't even given you guys time for questions. Are there any questions? Unfortunately, I couldn't hear you. I don't know if there are any issues. Are there any questions, really? Before I proceed, are there any questions? And that is a very nice question. Like, how can you ensure that the combination of student ID and the course ID are unique in the student course table? Now, with join tables, the uniqueness is never an issue, because now we are joining a relationship that has many to many kind of relationship. So one student can do many courses. It seems like, as you can see here, student with the ID of 1 is doing the course with the ID of 1 and the course with the ID of 3. So uniqueness is never important in the join table because there are going to be multiple instances of those entities. This is where the multiplicity now starts to exist. Whatever I was drawing at this particular point, this many-to-many bit. Yeah. So student and course. So this is where the many-to-many bit is. So uniqueness is never essential when it comes to building this. So I hope I've answered you. Yeah, uniqueness is not important for the join table. Are there any other questions? Humphrey, I hope I've answered you. Any other question? Okay. I'm hoping I've answered Andrew. Sorry, Humphrey. Now, we'll proceed. Now, with the third normal form, what is happening is that now we want to remove transitive dependencies. We want to remove transitive dependencies. So a transitive dependency is a dependency that does not depend entirely on the primary key. It depends on another field. So all fields are supposed to depend solely on the primary key, but a transitive dependency will not depend on the primary key. So we remove the transitive dependency. So the transitive dependency usually find them in things like, let's say, for example, the student had date of birth, date of birth here, date of birth field. I think I'll just add another column here. Then another. So now in this case, we'll have a date of birth for the student, and then we also have age. So in this case, the date of birth and the age, sorry, the age is dependent on the date of birth. It's not depending on that unique field. So we can derive age from date of birth. So we don't need to store age here. We can store it in its own value. So this is a transitive dependency. It does not entirely depend on the primary key. It depends on the primary key through the date of birth. So if date of birth here was maybe 2002, age I think would be 22 that way. Is it 22? Yeah, it's 22 that way. So age here depends on date of birth. It does not depend on registration number. So we can separate these details for age and the details for the date of birth and the age. We can have them in a profile table. So I'll add a row here. So it should have been after this. So we can have this one being a profile table this way. So this can be profile or biodata table. Let's call it bio data table that way. So there's date of birth, there is age. We can also have question also doesn't depend on this. So we can also separate this to become like how do you call it? In its own birth details table or in the age table, something of that. So that at least we separate the DOB from this, because in this table also biodata is not going to depend on the primary key. It's still going to depend on it's not going to depend on the primary key here. It's still going to depend on DOB. So you can move this one to maybe like an edge table, something of that. So that at least we have eliminated what that transitive dependency. So we can have like that edge details table that way. So most of the times we look at attributes that can be derived, then we separate them. So edge details should be maybe 1. So it's not 1, it will be the edge itself together with the ID of that particular student. So you can add edge details that way. Maybe this one is 22. This one now becomes 1. So now as you can see, edge details here, the edge is entirely dependent on this ID. But on this other case, it wouldn't be dependent on it. And also in this other field, it wouldn't be dependent on it. So in biodata, we can also add other details like address and the rest. So we are moving to more granular details. So address can be maybe Kisumu, itakuwa wapi tena? Yeah, that way. So biodata details, age details, and the rest. So we keep on separating until we can no longer separate it based on these normal forms. Now, one thing to also note is that before we place a table in second normal form, we must ensure that it is in first normal form. And before we place a table in third normal form, we must ensure that it has conformed to the requirements of the second normal form. So I am not sure if there are any questions up to that point before I proceed to the next thing. Seems to be no questions so far. So if there are not any questions, then I'll proceed. So that is how we'll do normalization. Should be the physical design. Now, the physical design, you notice that with the Logical design, I just added the attributes and the types in high level. Now, with the physical design, the first step is to identify a database. Physical design. So the first step, we identify a DBMS that we are going to use to implement this. That is the first step. So in this case, if we're using a relational database like identify DBMS. So in our case, let's say we have identified that we want to use a relational database. And then this relational database, the specific implementation will be Postgres that way. Now we have decided that we want to use Postgres. Once we decided that, now we port this implementation we have into the specific data types for the Postgres database. Now, in my case, I think I'll use this since it's more normalized. So we'll say we'll have, for example, for the student, we will have first name. So first name is going to be a varchar type. You can also say its limit should be around 30, and then it will not be null that way. So now we are being very, very specific with the reference to the architecture of that DBMS that we want to implement our design in. And then we'll have, for example, the last name. Then it's going to be a varchar 30, not null that way. First name, last name. Then we'll also have maybe email. So email is also a string. So it is not a string. Yeah, the registration number. So we'll have, I think this one belongs here. We also have the registration number, which is going to be an integer in this case. And then this registration number is going to be, let's say its length is going to be 7. And then it is going to be the primary key that way. So this one is going to be an implementation that is based on that specific architecture. So in this case, the architecture is the Postgres SQL database. So we've identified database management system, which is the Postgres SQL database management system, and then the implementation for some of these attributes that we listed here, maybe the name and the course, as you can see here, is now varchar, and then there is integer, and then maybe there could be a boolean, there could be a float, there could be the types based on whatever you currently want to implement it. Yeah, so before I move on to the next thing, I think just brush over what we've gone through so far, just list in high level. So don't know if there are any questions before I even proceed. James had a comment. Hey, James. Hey. Yeah, I think that is what we are doing here now. As I mentioned, when you're doing database design and development, it is a very essential step, since we'll be developing on the front end and on the back end, and then you're going to store the data in the database. So we are doing all of this because we want to manage this data, right? Data for our school management system, data for bursary, data for any application for a bank or anything. So if we get this database design wrong, if we get this step wrong, then it simply means we will not be working efficiently on this other specific tasks. So this is a three tier: the first tier, the second tier, and the third tier. So if you get things wrong here, then in these other tiers, we're going to really struggle with implementing some features. Now, as I had mentioned, when it comes to database design, there are three steps. There's conceptual, there's logical, and physical. Now, before you even get into the intricacies of what conceptual, logical, and physical is, it's important to understand what an entity is with reference to a particular domain. So an entity is just a real world object in that particular domain. So in this case, for a school, an entity could be a student, a teacher, examination, and department. So these are entities that exist within that particular institution. And then they are attributes of that entity. So what is this thing about a student that we want to store? We want to store the name of the student, the ID of the student. We want to store the course the student is doing. For the teacher, we want to store the name, the qualification, and the like. So that is what an entity is, and then also those are some of its attributes. So the entity is the real world object that is going to describe a particular concept in that domain. For example, a student, a teacher, examination, and department. Now, once we've understood what an entity and an attribute is, then we can go to conceptual design. So with conceptual design, it is a high-level design where we just list the entities together with the attributes. So in this case, there's a student, there's a course, there's a teacher, there's a department. So we are listing these entities and their relationships. Most of the time, we don't add the attributes here. So just list the entities and their relationships. So there's a student that has a relationship with the teacher. So one student can be taught by many teachers. One teacher can teach many students. That's why this is a many-to-many kind of relationship. The same with student and course. One student can do many courses, and then one course is being done by many students. So there's a many-to-many kind of relationship between the student and the course, and then the student and the teacher. For teacher and department, of course, there is a one-to-many kind of relationship, because uh, one department is going to have many teachers, and the teacher can only belong to a particular department that way. Now, for the student and the buyer, of course, there is a one-to-one kind of relationship, because a student is only going to have one buyer. So once we depict a relationship this way, then what we've simply done is we've done the conceptual design. We will set the entities together, the relationships among them. Now, the next step is the logical design. So in the logical design, we are going to list the entities, the attributes, and their types in high level. And then this is also where we do normalization. So I listed the student entity together with some of these attributes, the entity with some of these attributes. So this is a logical design. So we are being more granular with the details. So this student, what attributes does the student have? The student has a name, a course, an email, and a registration number. Now, I also say that we are going to do normalization in this particular step. So with the normalization, I also listed the steps. I mentioned that with normalization, they are divided into three steps. There's the first normal form, the second normal form, and the third normal form. So in the first normal form, we ensure that each instance is unique, identified by a primary key, and then each field should have an atomic value. So for example, for the name attribute here, I had to split it into first name and last name, because it was not a single value. Name was a multiple value, not a single value. So I had to split it into first name and last name, as you can see here. There's email also. There is now, of course, it only contains atomic values. So we've satisfied the first normal form, because each field has atomic values, and then for the atomic values for the different instances of that particular entity, they're identified by a unique, by the primary key, which is unique. So in this case, the primary key is the registration number. Now, for the second normal form, you're supposed to remove partial dependencies, or the repeating groups. So we will create a new table for repeating groups and join it with the foreign key. So in this case, we had added course here. But now the problem is that assuming one student wants to do multiple courses, and our table is designed this way, it simply means that we will have to repeat all the values of the student for each course that they want to do. For example, in this case now, if course was here, and as I mentioned, Alan Turing was doing multiple courses, it simply means we'll have to repeat all details of Alan Turing for each and every course that Alan Turing is going to do, which of course is not going to be efficient. And so we separate it into a new table, and then we join it using using a foreign key. So in this case, since it was a many-to-many kind of relationship, I use the junction table or a join table to join the course and the student. And so we add student course. So if Alan Turing does one course, we just add the course ID here. If he does another course, we just add Alan Turing's ID and the course ID. And then from this one, you can be able to get these other details that way. So that is with the second normal form. Now, with the third normal form, we're supposed to remove the transitive dependencies. So with the transitive dependencies, as I mentioned, there are dependencies that are not entirely dependent. There are attributes that are not entirely dependent on that primary key. So in this case, they depend on it, but they don't depend on it entirely. So they depend on it. They depend on it through another column. So like this one here, for the student and the biodata details, we added date of birth here and the age here. Now, age here is dependent on date of birth, but it's not dependent on the registration number. So it is not entirely dependent on the primary key. So we had to separate it into the biodata table. And then for this biodata table, we also had to separate it into age details so that we have the age and the ID here. Because date of birth here, we were able to retrieve age from date of birth. So it was not entirely dependent on what? The date of birth was not entirely dependent on the, how do you call it, on the age. So the age was not entirely dependent on the primary key for biodata. It was only dependent on the date of birth. So age here depends on date of birth. So if there's a column that depends on the primary key through something, that is a transitive dependency. So you separate it and place it in its own run. So the data will be normalized. Now, as a summary for normalization, what I'd like to say is that we do normalization in order to achieve two things. We want to reduce, we normalize data to reduce redundancy. Is that how we spell redundancy? To reduce redundancy and to, let's read apart from repeating it, is reducing redundancy. We have reduced redundancy, and we also eliminate anomalies that way. We eliminate anomalies, reduce redundancy and eliminate anomalies. So anomalies, I didn't mention it, but they're divided into, we have 4 kinds of anomalies. It's 4. Let me list them. We have the updation anomaly, we have the deletion anomaly, and we have the insertion anomalies. I think they should be 3. So with the updation anomaly, when we want to update some data, we are forced to probably update it in all other areas where it does repeat. Like in this case here, for the student name, for the student here, the name, the course. So now, if you want to update the name of this student, the name of this student here, and they are doing multiple courses, then it will simply mean that we'll have to update it in multiple areas in that particular, for that particular instance. So that is what the insertion anomaly is. So the updation anomaly is. Now with the insertion anomaly, when we're inserting one field, we also have to insert other unrelated or unnecessary data because we're inserting that one particular field. So like this case of adding, a student is doing a new course. So we will add a course, maybe business management. Then we'll also have to add the other details for that particular student, which is not necessary. So that is an insertion anomaly. And then there's a deletion anomaly. Now, this student is now doing a new course, an entirely new course. So we may find ourselves in a situation where we've deleted an entire course that is being done because that student that was doing it has also been removed from our system. That is an example of an insertion and a deletion anomaly. So to prevent those anomalies, we usually normalize our data. Now, as with any other thing, practice does make perfect. So the more you practice, the more you get good at normalization and database design. Now, I also talked about the physical design, which was the last step. And the physical design, the first step is to identify DBMS, a specific architecture implementation for that particular design that you've built. So in my case, I chose the relational database, which was Postgres. And then, of course, I had here the first name, the last name, and the registration number. And then I added the different types. So the first name is going to be a varchar based on this implementation here. And then it's not going to be null. So this one is going to describe how that data is going to look like together with all its constraints. So that is what the physical design will contain. And then we move to the actual implementation. Think the moment we've all been waiting for, the actual implementation. I don't know if there are any questions up to that point. Swali kweli. Hakuna swali? Yeah, normalization does affect query performance. It really does affect query performance. Because at the end of the day, it's going to be less costly to retrieve less data than to retrieve more data, because like in this case here, name, course, and the rest. Now, if this data is not normalized, then of course, what is going to happen is that when we are retrieving just that particular student's data, we'll have to retrieve more data as opposed to if you're just retrieving how do you call it, a single subset of data that is normalized. So normalization does affect query performance. It really does how do you call it, have an impact on the performance of your app also. Though sometimes it is negligible, just a few milliseconds, but it's going to cost less time, and it's going to cost less time to retrieve data that is normalized than to retrieve data that is unnormalized. So haya, na swali lingine, how do we balance the need for normalization with the need for efficient query performance? I think I've answered this question. Haya, sawa sawa. So sasa tutaendelea, we'll get to the implementation bit. Usually one compiler. Yeah, I'm going to use one compiler for my design. You guys can see this, So this is what I'm going to use for my design now. We've agreed that we want to implement this on what do you call it? We've now agreed that we want to implement this in Postgres as now I'm here. So now I'll port this specific implementation here. So I'll take this data here. This is what I'm going to create. I'm going to create the student course, and the biodata table. So I'll create table. So I'm using SQL now. Trying to get to SQL. Table student. Student is going to have a first name. First name is going to be varchar, 30 characters. Then it's not null. Then the student is going to have a last name, varchar, 30, and it's not null. Then the student will have a registration number. Registration number is going to be an integer. Integer. It's not null. Then does the student have email? He's going to have an email. It's going to be a varchar, 30 characters. Then not null that way, which is okay. So now let me run this. Our table has been created, so if I select everything from student this way, now of course I have my table and it has 0 rows. So I'll go to Mukaru and get some data. Mukaru. Yeah. So I'll get some data and use it to populate this. So we had registration number that way. So there's first name and there's last name. There's first name. I thought I was speaking and I'm muted. first name, last name, email. Should we add gender? Not really. So I'll add, let's say I need only 10 students and add it to be in SQL. And then the table name is student. And then of course preview this to see whatever I have. So I'll copy this. Then I'll bring it here. So I'll insert first is when I'll select it. So to insert data into an SQL database, of course, you can see insert into the table name, then the field, and then the values in the order in which you've passed the fields. Now, if I run this, now we don't have a primary key here because I've not added any field as a primary key. So I'll make this one primary key that way. Yeah, now it becomes a primary key. As you can see, we have this detail stored and so insert into. So if you want to select, then you have to select everything from it. This is a simple query. If you just have the if you just want the last name, then we simply do last name from student table. Now we just have the student's last name. So now we have this table. So the next one is the course table. So let me create the course table. So create table course namna hii. Before I get into course, I think I'll go with biodata first. So create biotable, biodata. So it's going to have hometown. So hometown, in this case, is going to be varchar. Then the varchar is going to be, let's say, 30 characters. And then we don't want it to be null. And then which other thing? Should I go with date of birth really? Let's go with date of birth. That way it's going to be a data type, and then not null. Then over to hometown and date. Let's say contact ya mzazi. It's going to be a varchar. Let's say 16 characters. That way. Yeah, this should be okay. That. Then of course now, let me just create this first. Then I'll select everything from biodata. Right, now okay, so we have hometown, DOB, and contact. Now there's going to be a relationship between student and biodata, which is a one-to-one kind of relationship. So we have to implement this in Postgres. So I'll create a field here. This field will be student ID that way. It's going to be an int that way. By creating this field, what I do, I'm going to add a constraint. So constraint, then constraint. So we'll have constraint, then I hope it's visible to you guys. Constraint, and then the name of the constraint. So I'll call this foreign key for student. Then it's a foreign key. So what is going to be a foreign key here is the student ID. Now, this student ID is going to reference, that is going to reference student, the student itself, and then it's going to reference the registration number that way. This should create the constraint. So the name of the constraint, name of the constraint, name of the constraint, and then the foreign key field here is student ID. Then it is referencing student registration number. Run that. I miss something. I miss something. Near at or now it's okay. Now we have the student ID. So to add a foreign key in Postgres, then there is constraint, and then the name of the constraint, so foreign key for student, and then the foreign key. Now, which field here is going to be the foreign key? The student ID. So we have the student ID here. Now, this student ID field here, which table is it going to reference? So we had references, and then the table name is student in this case, and then the registration number is the field that is going to be attached to that foreign key that way. Now we can add some details for the biodata. So we need hometown, date of birth, contact. So I'll come back to Nukaru. Then I'll select hometown. So hometown here is, so do we have city? Yeah, we have city. Then date of birth, DOB. Then it will be a date type this way. Yeah, let's just use that format. Forget about, don't mind so much with that. Correct. Then there is contact. So there is contact here, which is going to be, we have contact phone number, phone, that way, so that format I can buy. So hometown, date of birth, contact. So we have hometown, date of birth, contact, and then the student ID. So for the student ID, I'm going to have a row. So this row number, it's okay. So since there are 10 of them, they should be related. So I'll copy these ones this way, and then I'll insert it here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I run this. Hometown. Column hometown of relation student does not exist. Okay. Yeah. You know I do this mistake every time when I'm getting from Lukaku. So it should be bio. Data is the row you want to insert in. So I'll review this again. And then I'll copy this. Then I'll add that data here. Run this. Yeah, so now we have that data for our students. So now there's a relationship between the student and the biodata. I don't know if there's a question up to that point. It seems there is no question. So I'll proceed now. I want to perform a join query. I want to join those two queries. So the way you join is by you select everything from, let's say, the student table that way, and then let us do a right join. So you're going to write join on the biodata table. So by joining on the biodata table, you're going to join so on. So this on will refer to the column that is identical in both of them. So in this case, student dot registration number strictly equals registration number strictly equals biodata dot student ID that way. So this should give us all data from the right that are that have matching instances from the left. So if I run this, should be 1 equal sign, not 2. 1 equal sign. Take note of that, please. So I run that. Now I have this. So I have my first name, last name, registration number, email, hometown, date of birth, contact, and student ID. So now we've joined these two tables. So this query has taken data from the student table and the biodata table and joined them. So let's assume you only wanted the first name and the hometown. So let's say we need the student dot first name and then biodata dot hometown details. That way from student. So when I run this, now I only get first name and hometown details, and I can know where this student is coming from. As you can see, Nora is coming from, whatever this hometown is. Hendrik is coming from, whatever this hometown is. So that is how you can make a simple join query. So just a recap on the join query. We select whatever fields we want or everything from that particular table, and then we join with the other table we want to join. So it can be a right, a left, or the other join. And then when joining, we specify the attributes that are similar to both of them. So in this case, that foreign key for student ID is what exists on the registration number. So we're on this particular column. So with the right join, what happens is that we have, say we have this, we have one table here, and say we have one table here, then we have another table here. So we are taking everything from the right table together with all matching instances from the left table. So this is a right join. So in this case, whatever is on the right is student. And then whatever is on the left is biodata. So we are taking everything that exists in biodata, in student, and all other matching instances in biodata. This is a right join. You take everything from the right and all matching instances from the left. That is a right join. Now, that is with student and biodata. So you can see this syntax. So join, select from student, right join, whatever that other table is, and then you specify that matching field that way. I don't know if there are any questions up to that point before I proceed, because I want to get to the other thing, which is the many-to-many kind of relationships. Yeah, you can just post your questions here if you have any question. I think that is okay. So I'll move to the next thing, which is the course table. So now create table course this way. So this course has the course has an idea, which is a varchar 30. Not be varchar. Maybe mmenyamaza tu, mimi nifanya makosa. It's an int, varchar int, and then it is the primary key. I'm getting confused. I think I used varchar more than any other type. So ID is int primary key, and then the name of the course is going to be varchar 30 that way. I think this is what we had in course. Just the name and the ID, which is okay. And varchar, and then not null. Should not be null. That way. So now it's okay. And then I'll see how it looks like. Select everything from course. Of course, I missed this semicolon here. And don't forget it. If you forget, then becomes a problem. Then there's nothing like vrchar. There's varchar. And I run that. So you have ID and the name. Now let me get some courses from this other side. I want us to have only 5 courses, not so many of them. So we have course. So I'll use a custom list. So my custom list will have computer science, IT, and this sequentials. Yes, IT, business management. We'll also have law. We'll also have 1, 2, 3, 4. Too many we don't know. Let's see. Actuarial science that way. Is that how you spell it? Maybe. Then we have the idea. We have the idea. So this idea, I'll make it a row number because I only need 5 of them. So I only need 5 of this, and we're inserting in the course table. So I'll copy this. Yeah, this is okay. Then we run. Okay, there's nothing like course. It is the name of the course. I forget that. Then I copy this. And I keep on. Yeah, this should now be okay. Now if I run this, everything is okay. Now we have 5 courses: computer science, actuarial, and the other one. Now there was a many-to-many relationship between student course, between the course and the student, and so we use a join table to get the student course. So let me now add this course to the student course table. So I'll create the student course table. So create table student course. Student course is going to have the student ID, which is going to be an integer, not null, and it's also going to have the course ID, which is going to be an integer that is not null, that way. Now, the student ID and the course ID are going to be foreign keys, so you have to add that constraint. So I'll add constraint. So foreign key for the student is the name of the constraint. Constraint foreign key student, and then foreign key in this case is going to be the student ID, and then it's going to reference the student it's going to reference student table, then the registration number, that way. And then we had another constraint, since you have 2 foreign keys. Constraint foreign key course foreign key course ID references course, and then the ID of that particular course. Leave it. Yeah, so now these 2 are foreign keys, then of course we've added them. So let me see. table has been created. Then let us select everything from let's select it from here. Student course, that way. Then I run this, we should have the student ID and the course ID. So now let me get data for the student ID and the course ID. So this one is going to be a row number. This one is also going to be a row number. That way. Yeah, so let's say I want 5 should be enough. I'm going to preview this. Supposed to go to the student course table. This underscore course table. I preview this. I'll copy this, then I'll come and insert it here. Now we have the student with the ID of 1 doing the course of 1, with the ID of 2 doing the course of 2. So things are okay. So the next thing I'll do is that is okay. So now I'll do a join for these ones, for these 3 tables. So now, as I mentioned, the right join is going to take everything from the right and all matching instances on the left. So I'll select everything from student, and then I'm going to write join on course, go with student course, because this is where there's a relationship. Join on student course. So you're going to join on where the student dot registration number is equals to the student course dot student ID, that way. So now if we have a look at what this gives us, now notice we've gotten all matching instances from the right table and whatever is matching from the left table and any other thing on the left table, which is now everything, because we are doing a right join. Now if it is a left join, what we're going to get is see, now we get this one here. So we have all matching instances from we have everything from the right, so everything from the this other table, that is this left table, and any other thing from the other table, which is the student course table. So it looks something of this sort. So now in this case we now have student and student course. Now with student and student course, what has happened is that when we do a right join, we get all instances of student that match any records on the student course table. But when you do a left join, it now becomes the opposite. We get everything from the student table and all other, not all other instances, but only the matching instances from the student course table. That's why you notice here that these other ones are returning nothing, because we did not add values for them. So we get everything from this right table, and then any other matching, and then what do you call it, the fields from the matching fields from the other table. So these ones don't have a matching field, and so they just return nothing. So right join and left join is just a question of who is on this side and what are we getting from this side, who is on the left side and what are we getting from the left side. Now what we have here is just now the student ID and the student's details and the student ID and the course. But now what we want, if you want to know the course that that particular student is doing, So what I can simply do is a right join. So I'll do a right join here, which will give us only the matching instances. So once it gives us the matching instances, as you can see, now instead of just getting data from the student table and the student course table, now I also want to get data from the course table. So now I'll do another join. So now we'll do left join on course, the course table, not on comes later on. So then we left join the course table. So we also join it with the course table on course dot id equals student course dot course id, that way. Simple join. So now if we get this data, what will we have? Now we get the matching records together with the courses. So now of course we may just want the name of the student and the course. So we'll select student. From the student table we'll select the first name. To also we'll select the registration number, student registration number, that way. And then we want course dot name. So these are the only fields we are getting. We're getting the registration number from student, first name from student, and name from the course. Now if I run this, should get my output. Now I am able to get whatever that student and the course that that particular student is doing, as you can see here. So that is with joins. So we are almost about to finish. So I'll open room for some questions if there are. Superior white. How do you not use not null on int fields while creating a table? How do you not use? Hey, don't use. Which int? Yeah, you just simply add not null, because the not null constant just determines whether that field should be added or not. So in my case, the not null is determining that it should be, that field should be added. So if you don't add not null, of course it will be added. If you don't add not null, of course the field can be empty. But if you add not null, then the field cannot be empty. But for primary keys, by default they must be added. So we don't add the not null field. So just add primary key, and so you'll have to add it because it's the unique identifier. So you mustn't have that constraint. So I've answered you. Any other question? Any other question? No, any other question before I end the session? Kama kuna swali, like there's no question. Sawa. Kama kuna swali, mimi pia think I'll call it a wrap here. Don't worry, I'll share this. Let me share it just immediately. So share immediately, so at least you can go and experiment with it. So I'll call this AF Summit. Summit. This is how you spell summit. Summit dot SQL. SQL for African Summit. So create that secret paste. Yeah, it's okay now. So now this one is publicly available. You can go and experiment, test with it. I really joined this chat. Should be able to. Should be able to. So now let me add this one here. if you guys have gotten it. I hope you guys have gotten it. Natumai ya kuwa mmeipata, so that should be the link. That's connected.
Hi, Steve. I have shared it on the chat section. They should not be able to access it.
They should not be able to access it.
Yes, thank you.
So I think on my part I've come to the end of the session. I hope I have delivered everything I promised. Ama kuna yenye nimewacha nje. I hope sina deni ya mtu. Yeah, so I'll pass it back to, I hope Cassandra is around. Yeah, I'll pass it back to Cassandra. So Cassandra, you can take it over from here.
Wow, thank you so much, Steve, for such an incredible session. And sure, I hope you can hear me. Steve, am I audible?
Yes, you're audible.
Okay, so thank you so much for that wonderful session. And I'm sure we've all gained valuable insights into database design and development. So, yeah, we'll have another session in the afternoon at us from 2 p.m. and we'll get to know more about database design and development. Thank you so much, everyone, for attending. And kindly go to our socials go on X, formerly Twitter, and write something about this session, what you've learned, and some of the challenges that you've been facing in database development, and we'll engage there. Yeah, so once again, thank you so much for joining the session and see you in the afternoon. Bye bye.